right? So, you know, many examples, different areas, right? This cartoon of Harris is very, I think, to the point as far as we're concerned. Okay, so here's one of my favorite examples. This is the first gravitational wave detection by LIGO. And this is from the discovery paper, this figure. And you see this is the waveform, the strain, delta L over L, the fractional change in the arm length as a function of time. And this is at Hanford in Washington. And this is at Livingston, Louisiana. And here, what they've done is they've taken this waveform and superposed it on top of this one. Yeah, I know for technical reasons it's inverted, but that's just because of the geography of the two sides. They have to change the orientation of the detectors. But you don't have to do any fancy statistics, right? You can see by eye that these are the same waveforms, right? So these things are over 2,000 miles apart. So that's how we know that they saw a gravitational wave. They were monitoring the strain, and well separated, not a terrestrial event with a very high significance, they saw a gravitational wave. But how can they claim this wave came from two black holes, 30 solar masses each, that have been orbiting each other and then smashed into each other and produced this thing far away? I mean, the whole idea is preposterous, right? That nature would arrange to have, you know, not 5 solar masses, not 10 solar, 30 solar masses each, and have an event rate that was appreciable enough that on a NSF funding timescale, you could see events, right? It's crazy. So how do we know that this happened? And the real reason we know is because of simulations, right? From solving Einstein's equations numerically on a computer, you set up initial data with suitably chosen masses and spins, and you get, see the red here is numerical relativity. So what's done in the second part here is, first of all, this is smoothed in a certain way. So those of you near the front can see there's some width to the gray here that's supposed to represent some uncertainty because of the noise in the measurement. But you can see how well so this stands for simulating extreme spacetimes. That's the name of our collaboration that produced this particular waveform. And you can see from the match to this waveform, that's how we know it was black holes. And that's okay. Numerical relativity, so I just picked that because that's my field, but what I'm saying applies in general to computational astrophysics, right? That if you look back for any particular field of simulation, around the 60s is when universities started getting big enough computers that people could do interesting things. This is the first paper in numerical relativity by Hahn and Lindquist. And in modern language, this is the head-on collision of two black holes. And it's fun to read the paper. They did 50 time steps. This took 3 CPU hours on an IBM 7090. They had a grid. This was axisymmetric, or head-on collision, 151 by 51 grid points. And they evolved up to 1.8 M. So this is relative to units. So you can think of M of solar mass here. So a solar mass is 5 microseconds. But more important, the Schwarzschild radius is 2M. So this is roughly a light crossing time across one of the black holes. Okay. So not very far. And then they have this great conclusion. In summary, the numerical solution of the Einstein field equation presents no insurmountable difficulty. Now, actually, if you read the paper, the reason they quit after 50 time steps was their code blew up. So in fact, I would come to the opposite conclusion. It presents many insurmountable difficulties. So in fact, it took over 40 years before the full three-dimensional problem, say, of orbiting black holes could be solved. So the focus of what I'm going to talk about, I'm going to talk about the coming revolution, is related to solving PDEs, partial differential equations, right? So things like hydrodynamics, MHD, gravity, whether it's Newton or Einstein, radiation transport, you can add whatever your favorite set of PDEs in astrophysics is to this list. But in particular, I'm not focusing at all on n-body or Monte Carlo simulations, right? Because I'm really interested in moving to bigger machines, exascale machines. And the methods that work on these kinds of problems are not the relevant methods for PDEs. So if you work on one of these fields, right, what I'm saying is partly relevant to you, but not as much as if you did PDEs. All right, so here's the dirty secret. The dominant algorithm we've been using to solve PDEs is essentially the same one that Hahn and Lindquist used in the 60s. And that's true of all of these. It's finite differencing or finite volume. So for my purposes, I don't need to distinguish. I mean, finite volume is a special kind of finite differencing. So I just use the word finite differencing. There's no difference as far as I'm concerned. They both go back. Okay, so the first idea that it might be a good thing to look at more modern methods, right? It's not like applied mathematicians have been sleeping for 60 years. They've been developing all kinds of interesting stuff, right? It's that we as astrophysicists haven't been paying attention. So in numerical relativity, the key thing is to recognize that the solution of Einstein's equations are smooth in the mathematical sense, right? We don't have shock waves or surfaces of stars. And right, I mean, of course, yes, I know there's singularities inside black holes, but that we can avoid by various techniques. So if you have smooth solutions, then any numerical analyst would tell you you should use a high order numerical method. So that's in the sense of, you know, if you're making some Taylor series approximation, you should be out, you know, not just using some linear or quadratic formula, you should be using something of higher order because you get more bang for your buck then. Now the problem with trying to do that, so let's look here. This is supposed to represent grid points in some mesh that you're using to solve your PDEs. So if you want to get a derivative over at this point, a high order method means that you use information from several grid points in the neighborhood of this point. And then, you know, you can look in books and they give all these formulas with different powers of H and blah, 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 right? A centered formula, so that means that this is at the center of the stencil of points that you use to approximate the derivative. As you go to higher and higher order, that's a stable process. The coefficients that go into those formulas stay bounded. Whereas the problem is eventually you get to a boundary, right? There's some physical boundary typically of your simulation. And if you tried, you could look at the books or you could derive one-sided formulas. So you can get a formula for the derivative here that uses these points. But that's an unstable procedure if you try to go to too high an order. The coefficients get very big and they alternate in size. Right? And so you get huge cancellations, and this just doesn't, eventually breaks down. So the way we handle this in practice, if this is an interior boundary, right, you divide your grid up into subdomains, is we have another subdomain on this side, and we communicate the information that we need at these missing grid points, these ghost zones. We communicate that information to this processor so we can use a more centered differencing formula here, and we maintain the stability that allows us to use higher order methods. And now you can see where I'm going. As you scale to 1 million processors, this communication cost between all the different cells that you're using becomes prohibitive. You spend all your time communicating instead of actually computing derivatives here. And that's the battle, that's the key issue to deal with as we look ahead to machines that are coming in the next few years. So in the case of Einstein's equations, about 20 years ago, our group decided that we should take advantage of the smoothness and use what are called spectral methods. I'll explain a little bit more what spectral methods are, but in particular, spectral methods, instead of using uniformly spaced grid points, they use specially chosen grid points with a bunching of points towards the end. And it turns out that with spectral methods, you can approximate a derivative, say here, using all of these points to get a high order approximation that's extremely stable. Okay, so you get around this point, you don't need the ghost zones the way that you do okay, so our code that implemented this is called Spectral Einstein code, and it works extremely well for binary black holes. And the basic idea of a spectral method, it's what you learn when you learn separation of variables. You take your solution and you approximate it as a superposition of some basis functions. But instead of this going to infinity, because we're doing this on a computer, you truncate this, you keep n basis functions. And these basis functions are typically, if it's periodic, you use a Fourier basis. If it's not periodic, you can use polynomials, Chebyshev polynomials, Legendre polynomials. The details don't matter. So a spectral method is just the name that's given to how you evaluate these coefficients. You use the orthogonality of the basis functions. So these coefficients are just the projection of this solution along the basis function. That's the standard thing you learn in quantum mechanics or your E&M class when you took it. So what turns this into a good numerical method is the turning this from spectral to pseudo-spectral method, which again, not recent. Instead of doing an analytic integral here, which is very restrictive, you evaluate this integral by a Gaussian quadrature. Right? So a finite numerical procedure with some weights and some abscisses that you use, the points at which you evaluate your solution. So these are carefully chosen. There are books, there are functions, there are libraries that tell you how to get these, so this is all easy to do. So if you think about it, it's just like in quantum mechanics where theorists will talk about having a representation of the wave function either in position space or in momentum space. Here's the K labeling which of these things are. So it's like having two different representations. And the nice thing about that is, if you want to take derivatives, you can differentiate this expression with respect to x, because you can analytically evaluate the derivatives of your basis function. So that's essentially exact. But if you have nonlinearities, so if your right-hand side has, f squared, what you can do is you can just take f at the collocation point and square it. So you can go back and forth between the spectral representation and the collocation, the physical space representation, depending on which is more convenient. So that's the heart of the method, and it's well described. There are lots of books and so on that you can read about this. And the advantage of this is, as you get to large N, the convergence of the method is exponential. So exponential here means faster than any power law, any power of N. So you're used to, having like a second order finite difference method, meaning the errors go down as 1 over N squared. So you double the number of grid points, the error goes down by a factor of 4. Here, when you double the number of grid points, you typically get a factor of, 10 to the 5, 10 to the 10 improvement in your convergence. So it's really powerful in that sense. But there's no free lunch. The key thing is this is true for smooth solutions. Right, so if you have a shock wave, then what happens is you get Gibbs phenomena. Right? When you represent the discontinuity as a superposition of basis functions, you get oscillations and overshoot. Okay, so the spec code does do things like neutron stars, but for that part, we just switch to a traditional finite difference code, just like everybody else does. But we want to be able to include, even we numerical relativists need to include matter, right? As soon as we want to talk about neutron stars, like black hole neutron stars, neutron stars, right? This is the famous first neutron star event detected by LIGO. Here again, you see here's the strain data shown this time as in frequency. It's a spectrogram, frequency versus time. You see this rising chirp signal, which is the representation of the H of a binary inspiral. And these are counts from gamma ray detectors that were flying in satellites at the time. And you see roughly 2 seconds after the merger of the black holes, you see this gamma ray. Right, so a lot of excitement, all kinds of press releases about kilonovas, and they focus, of course, on the gold and platinum that's being produced. I don't know why there's such a resonance with the public, but anyway, maybe it was with the reporters. So we want to be able to simulate these, right? There's this, this field now called multi-messenger astronomy, where the idea is that you have some event. Let's say here is a black hole tearing apart a neutron star, and this emits gamma rays and light, gravitate, all kinds of things, and each of these messengers contributes to the picture we build up of what this event is. So ideally, we would like to be able to simulate this event and calculate not just the gravitational waves, but all of these other messengers. So that's the holy grail. Quite a long way off from doing, an a priori simulation of this, but it's nice to read. Okay, so what are the challenges for the binary black hole codes? Well, unfortunately, our experimental colleagues are good and the signal to noise keeps improving, right? So in the next event run will be, probably roughly a year from now. That's the fourth observing run. The event rate is going to go up probably to be 1 a day or even more. So that means if you have something interesting that you want to do a special simulation for, running a simulation that takes 3 months is just, not going to cut it. You need to be able to do better. There will be some events we can hope. So the signal to noise of that first detection was 25, roughly. So between that event and 04, we can expect the signal to noise to go up by a factor of roughly 4 or something, maybe. I don't know, 79 or 5. So roughly we need a phase accuracy over the whole in spiral and into the merger. It's very, I'm not doing this exactly, but a good rule of thumb is just take 1 over this. That seems to work. So 0.01 after, could be as many as 40 cycles when you're in band. That's beyond what people are doing today. Okay, so you would need to improve the accuracy. And then if you look ahead to future detectors, and even go as far as LISA, LISA will have a signal to noise for supermassive black hole mergers of 10,000. There's no way you can take today's numerical relativity codes, even the spec code, and get this kind of accuracy. Moreover, if you don't get that accuracy, not only are you wasting billions of dollars, right, because you're not getting the maximum science, you should spend a couple million on a few numerical relativists. but worse than that, there are all kinds of other interesting events that LISA will see, MREs, white dwarf binaries, all kinds of, cosmic extremes. Who knows what they'll see? This is going to be the dominant signal. So to see what's hidden underneath the signal, some way or other, you need to sort of be modeling that strong signal and removing its contamination on the weaker signals. And if you make a 1% error in the dominant signal, you're not going to see anything that's hidden underneath, right? So this is a real challenge. Spectral methods, despite their power, they get their power by basically having relatively few subdomains, right, areas of grids, and lots of grid points to take advantage of the exponential convergence. So it doesn't help you to have 1 million processors because the number of processors is set by just the number of subdomains. So that's not going to work. Now let's look at neutron stars. There it's even worse. The current computational errors on typical, say, neutron star merger calculation, depends how optimistic the people are and how big a computer they have access to. Roughly, 1 to 10%. Whatever, 1%. In fact, we can't even quantify the errors often, because often the way you quantify the errors is you run at increasing resolution, right? And then you can see how the errors are scaling. You understand from the algorithm how they should scale. You could kind of infer what the errors are. But that assumes that you're already in the convergent regime, right? Where this Taylor series behavior is done, right? Is dominant. You can use the first few terms in the Taylor series to approximate the error. We're probably not in that regime. So it's very hard. We just run with the most resolution we can afford, and then we publish that result, and we wave our hands a little bit about what the error is. And simulations take too long. However long for binary black holes are even longer for neutron stars, because you have all of the physics. But the real problem is the methods that we're using, these things that go back 60 years, do not scale to the next generation of machines. Okay? But first, before I get to that, this is astrophysics. What's wrong with 1% accuracy? You should be delighted to understand something to 1%, right? Well, there are many examples. For example, two neutron stars collide. They eject some matter. The matter is what produces the gamma ray burst and the kilonova and all these other things. But that matter is just roughly 1% or so of the total mass that you sent in. So if you have a 1% error in your calculation, you have 100% error in the properties of the ejector. Okay? So it's just, there's an example. If you do core collapse supernovae, the initial conditions for that collapse involve an almost perfect cancellation between the gravitational potential energy and the thermal energy of the core. Okay, and then there's this instability that leads to the collapse. If you don't follow that small difference between two big numbers to better than 1%, you have 100% error in the outcome. Right? You've probably been to talks about core collapse supernovae, and you know that every few years the person presenting the talk changes from telling you the simulations explode, whoops, no, they don't explode, whoops, they explode. It's this problem, right? Not just you have to get the physics right, you have to get the numerics right. There's a goal for LIGO and gravitational wave detectors in general to say something about nuclear physics by looking, as the neutron stars approach each other and get close, there's a tidal deformation which saps some energy from the orbit and therefore speeds up the merger, so you cycle, the waveform is a little faster, phase evolution, than if it was two black holes. And from that, the amount of that effect depends on the tidal deformability of the neutron stars, which depends on the properties of the nuclear matter, the nuclear equation of state. So there's this dream of measuring equation of state properties from tidal effects. Well, the tidal effects are small. Right? You need to resolve the surface of the star to probably better than 1% in order to do this. And as the detector sensitivity improves, the problem becomes more and more acute. And then, of course, there's the cases where you get completely wrong physics if you don't have enough resolution in your simulation. Right? So if you have an instability like the MRI, the magnetorotational instability and accretion disk, if you don't have a fine enough grid spacing, you don't even see this instability. You'll conclude your disk is stable. Right? You just completely wrong result. So it's exactly these kinds of interesting problems where you do need high accuracy despite it being astrophysics. All right, and it's hard, right? The solution isn't smooth. You have surfaces and shocks. You have multiple time scales. You have multiple spatial scales. So you want to have an adaptive grid resolution. The geometry of the problem changes. You could have a disruption of a neutron star as it spirals into a black hole. There's a merger. You started with two objects, you end with one. Maybe you form a black hole out of a collapsing remnant. And then, of course, there's multi-physics. Now you want general relativity, you want hydrodynamics, MHD, neutrinos, photons, nuclear reactors, right? We're insatiable in our greed to add physics. So how are we going to deal with this? What's the answer? All right, so I'm proposing one answer. Okay? It's called the discontinuous Galerkin method, right? DG for short. And you notice at least I have the modesty to put a question mark here. It's a little, this is meant to be tongue-in-cheek, right? So I'm not saying this is the answer, right? I should probably say this is the answer that our group is pursuing. All right, so let me explain to you very quickly what this is. So a finite volume method. So here I've shown 3 cells in a one-dimensional grid, and we approximate the solution. We have essentially one grid point. You can think of it as being at the center of each cell. So there's some constant value across the cell that represents the solution. So here's in green is the true solution, and we're approximating it by these horizontal lines. Okay, so now you notice that the boundaries here, there is these things don't match, obviously. But these things physically talk to each other via conservation laws. Right? So for example, the mass in this cell can change if there's a density flux from this cell into here. The mass in here goes up, right? So we need a recipe, a prescription, which tells us how to update, say, the mass in this cell because of flux coming in and flux going out. And if we do that badly, we get the analog of Gibbs phenomenon. But there, we've had 60 years to figure this out. There are very good prescriptions called, limiters is the generic name given to how you do this, which can handle shocks. The problem with this method is if you want high order, you only have one grid point here. So to get high order, you have to couple together. You have to get information from not just the nearest neighbor, but it could be several neighbors away. And that hurts you when when these other cells might be living on different processes and you have to communicate information. That's a very slow part of the process. In a spectral code, the solution is expanded in a local basis. So here I've shown constant and x, a linear, right? The first 2 terms of polynomial of degree 0 and degree 1. But again, you go to higher order, right? So here's the solution, the same green, but now approximated by a straight line with an offset, right, to make a good approximation. Okay, so this will give you exponential convergence in smooth regions as you increase the order of this polynomial. But the flux here can't do shocks. You get Gibbs phenomenon. The DG code tries to combine these 2 things. The solution is expanded in a local basis, just like in a spectral method. But the way it's done, you're allowed to use exponential, so you still get exponential convergence if it's smooth, but this formulation allows you to use more general limiters based on the ideas of the finite difference ones that in principle can handle shocks. I think I'm going to skip this, some equations. All right, so we have a new code, which we've called Spectre. Some movie makers paid us a lot of money to use this name for some movie. I've forgotten what it was about. Anyway. Key thing is Moore's law is broken. Moore's law in the not actually as it was stated, but in the idea that the speed of processes doubles every 18 months or 2 years. Those days are over, right? The size of a transistor on a on a modern computer chip is, a few dozen atoms, 50 atoms or something on the side. Maybe you'll get another factor of 2, but it's just not going to keep doubling. The way that new machines are more powerful is by just having many processors. So here, this is actually this is from 2012, but I couldn't find a more modern picture that showed what I wanted. So this one is nicely labeled. So PU is processing unit, and you see that they go from 0 to 17. So there are 18 processes here. One of them handles I/O, and 16 of them are devoted to actually doing floating point operations. So 16. Does anybody know why there's an extra processor?
Failure.
Yes.
What?
Failure mode, right? So they generate these chips, by the thousands, and not all of them are perfect. So they design them to have a spare processor. And then as long as the 1 plus 16, 17 out of the 18, as long as 17 out of the 18 actually work, they can use the chip. So it turns out that's cheaper than throwing away every one that fails. All right, so modern machines, those of you who worked on Terra and so on know that, it's not 16 anymore, it's 128, 256. I'm not talking about GPUs. Okay. So why can't we take our current codes and run them on millions of processes? And it's because of the way we parallelize things. We have our spatial grid, we divide it up into subdomains, and then we distribute the subdomains to different processors. And then all the calculations that have to be done on one particular subdomain are handled by that processor that it resides on. Okay? And if it needs to communicate with neighbors or other things, then there's use MPI or something to either send or get information. Now, most of the time, while the communication is going on, the processor is idle. It's not doing anything. You actually have to go in by hand and code in a special way. There are even people who code in machine language, can you believe? Some hydrodynamics algorithm. So that while the communication is going on, the processor can do something. That's not a way to make a living, sorry. And then you have a load balancing issue, which means that different processes can be doing different amounts of work. You might have adaptive mesh refinement, different number of grid points in different subdomains. You might be inside a turbulent neutron star on one subdomain, whereas you could be in vacuum propagating gravitational waves out to LIGO on another process. So you might have to find where the location of the surface of the black hole is, because you need to excise singularity from your domain. So you're finding apparent horizon. You might be tracing light rays to do radiative transfer, or maybe neutrino pairs. Okay, so all of this different kinds of physics is going on. And typically, right, we choose a time step, and then we evolve the processes, all the subdomains by that dt. And then when they've all gotten here, we do the communication to take the next time step. So you can see whichever is the slowest process here will set the scale, the time scale of your evolution. And in the worst case, you might have one processor that you're waiting to finish what it's doing. and 999,000 other processes are sitting there idle, right? You're wasting the whole machine. And that's what will typically happen. This is what typically happens. So when we profile our spec code, and we have a particularly bad domain distribution, the top process in terms of CPU time can be MPI wait, right? Which is MPI telling you nothing is happening. Okay. That's bad. All right. So what's the solution? How are you going to, and the problem is worse the bigger the machine, right? Because there are more processes that you have to somehow find. So we have a solution for that. It's called task-based parallelism. And this is, I think, the real, the DG method is nice. There could be other alternatives. But this is something that I think everybody should pay attention to, even if you do Monte Carlo or n-body, right? You should think about this. It's a new way of thinking about doing parallel programming. New to us, right? Not new to computer scientists. Right? They've been thinking about this for a long time. All right, so the conventional parallelization is you have a bunch of tasks that you want to do. You know, compute the spatial derivative in the volume of some subdomain. Compute the flux term, send the flux to the neighbor, receive the flux from the other, from the neighbor. Whatever the tasks are. They can take different amounts of time, okay? And when the last one is done, you're now ready to take your next time step. So this is wasted time in terms of what you could be doing. In task-based parallelism, you design an algorithm where you think of each little piece of the computation that can be done on its own as a task. You have some supervising program which maintains a queue of tasks that need to be done. And then whenever a processor becomes available because it's finished its task, it gets any of the tasks that's ready to be executed will be executed. So what's hidden in this is a lot of clever computer science about how you actually do this, how you do the bookkeeping, and how you make this efficient. Right? That's not something I would advocate for a typical physicist, even one in such a distinguished audience, to do. Okay? So you should rely on, just like you don't write an MPI package on your own, you shouldn't write this on your own. So this is relatively new. There are no standard packages. You could do it yourself with a combination of MPI and OpenMP. I don't advise that. HPX is an example of a small group at a university doing something. The problem with this is bleeding edge code. It's not stable. I don't recommend that. The only package that we found that is mature enough to do it is Charm++, that comes out of a group at Illinois, University of Illinois, has a big user base. There's a cosmology code, there's a chemistry codes, there are a bunch of codes that use that, and that seems very good. So here's an example of a standard test problem in MHD that we ran a little while ago when Blue Waters was still around. It was the biggest machine that we could get access to easily. This was a relatively easy problem in the sense that it was a homogeneous computing load across the processes. So we took a fixed size problem, and then we ran it from a small number of cores all the way up to fill the machine. Roughly, this was roughly, depends, either 300,000 or 600,000 cores. I can never remember because this thing had hyperthreading, which was the relevant. But more than 100,000, right? And the fact that you get essentially perfect speed up tells you that this is scaling. And the only thing that stopped us was the size of the machine. So this is encouraging. It says we may be on the right track here. All right, so this is what task-based parallelism looks like if you profile it. So this is just a simple relativistic MHD test, 10 time steps. So the colors represent different procedures, different functions being called, like compute derivatives, compute fluxes, things like that, communicate things, and so on. So that's what these colors represent. So there should be 10 of them here. The black is the overhead. That's the penalty you're paying to run Charm++. So that's it here. The white is idle time. So you see at the startup, not all the processes are busy, right? But then as they get going, you settle into this pattern where there's no white. Everything is busy. Okay, and then at the end, as you finish, the machine shuts down, right, and you get this. All right, so our goal is to get something like this, you know, with 90% of the machine being used efficiently with no white. Now, I mentioned adaptive mesh refinement, right? You want to use fine grids where things are changing rapidly, and coarser grids where you can afford to. But if you're doing explicit time stepping, you have this Courant condition to worry about. There's a minimum delta t, which is in order of magnitude set by the delta x, the size of your spatial grid. So when you do adaptive mesh refinement, there's a smallest delta x, and there's therefore a smallest delta t that you have to use. Now, for efficiency, what you would like to do is only use that delta t where you need it, and take bigger time steps in other parts of the domain. However, if you do that, your code doesn't scale very well, right? Because while you're waiting for the fine grid to take its time steps, you could take big delta t's, they're sitting there doing nothing. Right? So that gives you bad scaling. With task-based parallelism, you can avoid that, right? Because what you do is you have those other cores do some other useful task, while where the delta t is small, you advance that. All right, so here's it's not a secret, right? Again, if any of you are submitting proposals for time on Exceed or some other machine, what you do, right, they ask you always, show that your code scales on Expanse or Frontera or whatever your machine is. And so what you do is you run your AMR code, but you use a global time step that's equal to the smallest one. Then you get perfect scaling, right? Because, you know, if you double the number of cores, it's fine, right? It all works. But in fact, typically what that means is you're using roughly 10% of the machine, typical applications, right? Because you didn't need to take such a small time step everywhere. Okay, but for some reason, the computer allocation committees haven't figured this out. Yes. Of course, when you're on the allocation committee now, you'll know. Right, so there was a survey of these AMR packages. The scaling was bad if they had local time stepping. There was one exception, and this is a code. All right. So lies, damn lies, and statistics. This is a quote that was popularized by Mark Twain. But in my case, I want to adapt it to limiters. So I'm going to come back to, I told you that the DG method had the ability to handle shocks because you could use limiters adapted from finite difference. So you go to the literature, you can find all these things, and they show nice plots and so on. Don't believe them. Okay, they're just not, for our purposes, they're useless. All right, so here's an example. This is a standard sort of test case. It's a cylindrical blast wave. So you take a high density cylinder of fluid with a low density outside. You put a magnetic field on just to make it interesting to break the symmetry. So there's a magnetic field, I think it's horizontal. And then you let this thing expand. So there's a shock wave where the high density propagates into the low density. Now, if you look at these four pictures, these are done with the standard limiters for DG that are in the literature. Right? So this is a variation on min-max limiter. These are based on the Weno, H-Weno limiters. This is another one. You can see they're terrible, right? There's all kinds of oscillations and non-monotonicity. These are very good. Okay? And what these are, you see it's DG, FD. It's a hybrid between discontinuous Galerkin and finite difference. The way it works is, I'll show you here. Oh, sorry, I'll show you in a minute how it works. This is another test case. So TOV is a Tolman-Oppenheimer-Volkov. It's a relativistic spherical star. And then again, to make it interesting, you add a magnetic field. So you have to do this in MHD. And this is using that limiter that I said was good. And these vertical lines. So what you do is you set this up. It's supposed to be in equilibrium. B field is a small perturbation. And it's not a perfect equilibrium, it's an analytic infinite resolution equilibrium. So when you put it on a finite grid, it oscillates a little bit until it comes to equilibrium. And these vertical lines are the known frequencies of the lowest few modes of oscillation. And you can see the nice, we can pick out the frequencies here, maybe at least 3. I don't think the 4 is really there. So that's a test of how good your code is at resolving this kind of thing. It's one way of testing. And adding the magnetic field doesn't, you can still do it here. The magnetic field is not important dynamically, but it does stress the code because the B field is strong. All right, let me show you quickly a movie. So this again is this combination. Right? And so the little black squares are where the finite difference code is being applied. And you can see it's only at the surface. Okay, and so you get a nice sharp boundary, which will be completely smeared out if you use a bad limiter. All right, so what's going on is you try to do DG. So you start with, you compute, this is at time n+1. You then check it. So TCI stands for troubled cell indicator. That's your psychotherapist who diagnoses whether this solution has too many oscillations or gives a negative density or something. If it succeeds, you don't apply any limiters, you just accept it as the new step and go back and repeat. However, if it fails, you then project it onto, this is now within each cell, you lay down a finite difference grid that's roughly double the resolution of the DG grid. You project onto those points, and you use a finite difference step over here with with these very robust limiters that we know from doing finite differencing, we then test that to see whether it's good enough to send back, restrict it back to the DG grid and do the DG whenever we can. If it's not good enough yet, we go back and do we keep doing finite differencing until, for example, a shock has propagated out of the cell. Then typically we can go back and do this. So this idea of a subcell, where you're using a different special purpose numerical method, is, I think, the way to make this all work. And that's how we got this good test result. You'll see we're doing things like real accretion disks and binary neutron stars and so on. This method, hopefully, will have some results to show. Okay, so, just to summarize, all right, enough is enough. 60 years. Okay. It's time to open our minds and think about other numerical methods that may be appropriate to the hardware of today. Algorithms like DG are high order, they're local, they only use nearest neighbor information, so you get good scaling. The limiters in the literature are poor. You should use, I think, a subcell method, which is a hybrid. And task-based parallelism is, I believe, crucial to being able to use the big machines efficiently. There will be some problems, very homogeneous problems with very limited communication, which will work out of the box on big machines. Most stuff that we do will not. And if you want to find this is all open source. You can come see the current state of the code. Thank you.
Questions for Saul? I'm also on Zoom here, so if there are folks online with questions, just raise your hand.
How do you actually do the testing for the reconstruction, whether you go to finite differencing, or what's the actual criteria?
First, I'll tell you what we use in a second. Just let me say that there are many prescriptions in the literature, many things you try. So what we typically do is, so in the DG method, we may have, say, 5 or 6 points in a subcell. So that's enough to get, say, of order 4 or 5 spectral coefficients of basis functions. So we just look and see if they're falling off sufficiently fast. If they're falling off sufficiently fast, that means we're exponentially convergent. So that's good, we keep it. If you have Gibbs phenomenon, then what you find is the high order coefficients, instead of getting small, they're just as big. So that tells you you have oscillations, and then we switch to finite differences. So that's what we typically do.
So you're basically trying to just see if there's a Gibbs phenomena happening, and that you deduce from the finite difference stencil coefficients.
We reduce from the basis.
Sorry, yes,
spectral
exactly.
coefficients.
Yes. Yeah. Thanks.
So I'm curious about the subgrid finite difference.
Yes.
A lot of DG methods have really attractive physics interpretations, particularly with independent time steps. You have like little cells that have some momentum flux into the big cell, and it stores it up over many time steps and then discharges it when it goes to evolve the big cell, and so on and so forth, usually associated with conservation laws. When you transition to the finite difference dynamics, you must just chuck all that out the window, right?
No.
So what happens? You must have to pick that a very special finite difference.
We use special finite difference methods that are conservative.
Okay, and it's possible to do that.
It's possible to do that, and in fact, not only is it possible to do it, but in Niels Deppe, who developed this for us as a grant in his thesis, he has actually derived some new methods that not only are conservative, but they're adaptive order, so that in the finite difference parts, you can actually choose whether to use a third order method or a fifth order method, whatever it is. I think there's a lot of scope for innovation in these techniques.
Thanks.
Yeah, so it's something that was interesting to me that struck me about how the adaptive methods are able to capture sharp differences, but also smooth functions. And it reminded me of image reconstruction for interferometry. And I was just wondering if you thought about how, if this could be applied to that, or how easily. When you have the sort of thing that I'm thinking of, for example, is if you're imaging a disk and then there's a sharp discontinuity in the disk, so it's sort of smooth, but then there's an edge.
Right.
Point source.
So I'm not sure that finite differencing. See, the reason we use finite differencing is because we want to do a time evolution where we have moving discontinuities. And so we need something that can handle that robustly, and that's what we use as limits. In image reconstruction, it's more a static problem, right? You have a sharp edge somewhere that you want to resolve, but you have infinite time to figure out how to do that, and it's a fixed location. So typically the methods that are used there involve, so typically your image might be represented by, say, Fourier coefficients. Because that's what you get out of a radio telescope, for example, right? So the Fourier basis is a bad basis for the discontinuity. That's where Gibbs' phenomenon originally comes from. So what you typically do there is you change your basis. You represent the image not as a superposition of Fourier modes, but you use something else that is able to capture the discontinuity sharply without. Right? So it's a transformation of basis that usually underlies those methods.
I guess I'm thinking of a situation where you have perhaps two things going on. You might have a smooth background for a part, and then a sharp edge or particular point sources with a relatively smooth, sort of a gas.
So again, I think fundamentally it's either you subtract out the discontinuity, as a step function. So you fit a step function and subtract that from the data and hope the remainder is smooth, and then you can do that, or you change the basis. Those are the two things I know of how to do.
I had a follow-up question to both the limiters and the local time stepping. I remember that in the past people were suggesting to combine both. This is that you basically use like an aider stepping with a predictor step, apply the subcell limiter just to that and communicate on the electron. Right. Is that something you're doing also in conjunction with
So in the subcell business, there are two classes of the way you do it. They're called a priori and a posteriori, right? So the a priori one is you try to, before you take a step, you try to figure out whether it's going to be good or bad, and then you switch if you think it's going to be bad. Well, there, since you never get it right, there's some inefficiency. So the a posteriori, which is what we've implemented, is you always try the DG step, and then you inspect it to see if it's bad. And if it's bad, you actually throw it away and go and redo it. And that seems to be, even though you're kind of wasting the thing, on average, that seems to be better. So I haven't looked in detail at these aider type things about whether there's a way to combine those two ideas.
Let's take one more question.
Someone else. So from what I understand you're still doing cycling and time step. Should I worry, like, does DG and FD, like, resolve the typical interpolation problem that we have when we use different time steps for different resolution and we need to interpolate things on the same grid?
Right. So it's not that they resolve it. You have to design a time stepper that will take care of that. So there was I flashed by a thesis project of my student Will Throw, THROWE. So you can look up, he has a paper in Siam Journal of Computational Science, where he designed, so the problem is if you go to the literature, the whole literature on local time stepping, again by applied mathematicians. So typically they are either at most second order accurate and conservative, or they're higher than the second order, but they're not conservative. And for us doing hydro MHD, conservation is crucial to maintaining stability of the solution. It's not just it's not just conserving to truncation order, you want to be conservative to machine precision if you can. And so Will designed an algorithm that is in principle arbitrary order. You can make it as high order as you want. I mean, it may not be useful to, I'm just saying in principle it's any order, and is conservative. And he had to figure out how you do the interpolations to keep those properties. And so it's one of these things which is an important contribution that only a few aficionados will appreciate, but it's actually a very important